For the introduction, torque is a force that can cause an object to rotate about an axis. When the object is subjected to a torque, it will acquire an angular acceleration. There are two types of torque, which is static and dynamic. When the object does not experience angular acceleration when it's applied with torque, the torque is applied is the static torque. Meanwhile, a dynamic torque will cause the object to experience angular acceleration. The angle of twist, also known as the twist angle or angle of rotation, is a fundamental concept in mechanics and structural engineering. It refers to the amount of angular deformation or rotation experienced by a structural member, such as a shaft or beam, due to the application of a twisting or torsional force. Understanding the angle of twist is crucial for designing and analyzing structures that are subjected to torsional loads, as it helps ensure the structural integrity and safety of various engineering applications. Lastly, modulus of rigidity is defined as the ratio of shear stress to shear strength in a rigid material experiencing an external force, shear or tangential. The value of modulus varies from different materials. For this experiment, the objective is to identify the relationship between torque and the angle of twist of circular cross-section bars, and also to determine the modulus of rigidity of certain materials. And for the scope, we use three different types of rods, which are aluminium, copper, and steel, which each of them has a 5.77 radius, 4.94 for copper, and 6.03 for steel. And then we apply a different length of rod in this experiment, which are 200 mm and then 400 mm. The radius of the pulley is 115 mm. And lastly, we apply different weight to the solid rod from 5 Newton to 25 Newton.
There are few theories that are used for this experiment. First, torsion. Torsion is an important structural process that improves member shear strength. It occurs when something is twisted, causing torque to be exerted on the member. Next, shear stress. It occurs when parallel forces are acting in opposing directions, added to the initial shear stress caused by the lateral and vertical applied stress. Next one is shearing strain. In theory, the shearing stress strain of a material under torsion is seen to be maximum on the outer surface and minimum at the central axis, resulting in the length from the center of any point in the circle of the shaft. Then we have torque and angle of twist. We will use these two equations in this experiment. So torque is equal to length of the moment arm and applied force, and angle of twist is equal to torque multiplied by length over polar moment inertia multiplied by modulus of rigidity. We will use the equation of angle of twist to calculate the modulus of rigidity.
This is the experimental setup of this experiment. Figure A show the machine and the setup, and figure B show the type of solid bar used, which is steel, aluminium, and nylon.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hanan Delisha and I will be presenting about the procedure. So for the first step, the radius of the pulley and all three bars was measured to calculate the torque and polar moment of inertia. So the diameter for copper was 6.03 millimeter, and for steel is 4.94 millimeter, and aluminium is 4.77 millimeter. For the second step, the aluminium bar was secured at one end in a fixed clamp and the other end in a pulley with the measurement of 200 mm and 400 mm to ensure it is held tightly to prevent movement. So you can tighten the fixed clamp with the screw given in the lab. For the third step, the rotation scale and pointer at the pulley end of the aluminium bar were adjusted. Ensure the pointer is aligned with the zero mark before applying any load, so we will get the actual angle of twist. And for the fourth step, repeat step 1 and Step 1 to 3 were repeated when applying weights from 5 Newton, 10 Newton, 15, 20 and 25 Newton to the pulley at the end of the bar. Last but not least, the fifth step, the angle of twist at each weight increment for both bar lengths were recorded, and then for each weight applied, the corresponding angle of twist was also measured and recorded. And lastly, step 1 to 5 is repeated with steel and copper alloy.
So the safety procedure applied to this experiment is firstly, we need to wear covered shoes to prevent injuries to the feet. Secondly, handling the bars with care is essential to prevent slippage, injuries or damage to the hand. And lastly, wear a lab coat while conducting experiments in the laboratory.
So here are the data collected for part 1, that is aluminium bar. We can see the angle of twist from the torque that is applied to the shaft. From the data recorded, we can make graph angle of twist against torque. So we can record the gradient line. So we can calculate the modulus of rigidity.
Assalamualaikum, my name is Hana Delisha and I will be explaining the calculation in results. So for part 1 in aluminium bar, it is shown that in the graph, the gradient for 200 mm is 0.0257 and for 400 mm is 0.0514, and the J is 1741.1, and so we can find the modulus of rigidity from the gradient, which is the gradient will be equal to L over Jg. So when you substitute the value, you can get the modulus of rigidity, which is 4.46 times 10 to the power of 9 Newton meter square. Same goes to 400 millimeter. It gets the same value.
So here are the data collected for part 2, that is steel. The angle of twist for this bar seems to be lower than aluminium. So the expected modulus rigidity will be higher than aluminium.
So for the calculation in part 2 with steel bar, the shown gradient in the graph is 0.0203 for 200 millimeter, and for the 400 millimeter it's 0.0416, and the J is 935.46. And same step goes with steel bar. We can use the gradient equal to L over Jg, substitute the value, and we get 1.05 times 10 to the power of 9 Newton meter square. And same goes to 400 millimeter.
And lastly, these are the data collected for the copper bar. After getting the modulus of rigidity for all three bars, we compare it to the theoretical value of modulus of rigidity to calculate the percentage of error.
So for the discussion part, the angle of twist formula can be written as this. Based on the equation, the angle of twist is directly proportional to the torque applied on the rods. According to graph 4.1, 4.2, and 4.3, the angle of twist is directly proportional to the torque applied on the rod. The formula of twist is verified for aluminium, steel, and copper rod. By comparing the gradients of each graph, it is possible to deduce that the aluminum rod has the steepest gradient, hence the lowest modulus of rigidity, meanwhile copper rod has the lowest gradient, indicating that it has the highest modulus of rigidity. A greater modulus of rigidity value suggests that it will retain its shape and a substantial force will be required to deform it, whereas a low shear modulus value indicates that the material is soft and flexible. As a result, we may conclude that aluminum rod is more elastic and flexible than steel rod, which is followed by aluminum rod. So from the equation, we can see that y equals to mx plus c as usual, and then the angle of twist is equals to length of the shaft over polar moment of inertia times the modulus of rigidity, and then bracket times torque that was applied on the shaft. The gradient of the graph is equals to m equals to L over jg, which is the polar moment of inertia times modulus of rigidity. So when we rearrange the equation, we can see that modulus of rigidity is equals to the length of the shaft divided by the gradient of the graph times the polar moment of inertia. So the experimental modulus of rigidity is calculated using the gradient of the graph. And this is the percentage error that we obtain based on the value that is calculated and recorded in table 5.1 using the formula.
So in conclusion, the objective of this experiment, which is to determine the relationship between torque and the angle of twist of a cross-section specimen and to determine the modulus of rigidity, G, of the materials, have been achieved. It is conducted that angle of twist is proportional to the torque applied to the shaft. The greater the torque applied, the greater the angle twist of circular cross-section specimens. The modulus of rigidity, which is G of each material, also have been determined, which are for aluminium rod is 4.46 times 10 to the power of 9 Newton per meter square. Steel rod is 1.02 times 10 to the power of negative 9 Newton per meter square, and copper rod is 3.11 times 10 to the power of 9 Newton per meter square. Shear modulus or modulus of rigidity, which is denoted by G, is a measure of the elastic shear stiffness of a material and is defined as the ratio of the shear stress to the shear strain. From this experiment, it can be concluded that the steel rod is more elastic and a flexible material than the aluminium rod and copper rod, since it has a lower value of modulus of rigidity. In summary, it can be said that steel, which is a brittle material, can be fractured at a lower angle of twist than the ductile material such as copper and steel, since it has lower torsional rigidity, modulus of rigidity, and shear yield stress.